Okay. So last time we talked about 3 different I/O. Um, let me see what. Okay. Oh, I think something's wrong because when my settings not right, it should be displayed on monitor 3. Yes. Okay. That's it. Okay. So we first talk about the one of the I/O is called programming I/O with pooling, and then the other one is program I/O with interrupt, and then the I/O with the um, DMA. So now, if you try to see the overall picture of these I/Os in the whole computer system, now if I can draw this very brief diagram. Here's the CPU. That's one of the important component in the computer system. Main memory. Okay, you have to apologize me because someone is working in my house because there was some problem in my house, so they just come. So the CPU is connected to the bus. Memory is connected to the bus. Of course, in most of the computer system, um, there's a dedicated high-speed connections between CPU and the memory. So in most case, the communication between CPU and the memory does not go through the bus. Okay, so it's a fast connection. So that's most of the modern computer system actually does. And then for any kind of component, like for example, the hard disk, and then it's connected to the bus through the disk controller. Okay, and then here there are a lot of registers. Remember, we have one of the registers is a buffer, right? And then we have a status register, busy register. We have a opcode, and then we have operands. All these different registers. Just remember that something we just talked about. You know, opcode, operands, busy register, and also the status registers. So this is the connection between the actual disk and the controller, and then the controller is actually is connected to the bus. Now, if you have a monitor, then we have also the controller, monitor, controller, or sometimes we call it graphics card, right? So it's connected to the computer system. So when a program is running, any program is running, and it's loaded into the memory when it is running. So when any of the actually process program request for I/O, so it can actually trigger the driver. The driver is a piece of software also in the computer memory, and when the program actually call the driver, and then the driver going to basically ask the CPU, say, okay, please do something. And then depend on what you want to do. If you want to do the import, then basically the CPU going to actually send the read. Okay. Oh, okay. First, the CPU going to check, check the busy register, right? Check the busy register to see whether the IO, the disk is really busy. Okay. If it's not, so the busy register says it's false. So then, so the CPU going to put the data, the operand, and the opcode. Okay. Opcode, operand, operander. Okay. So the opcode is going to be something like writing, write. Oh, I'm sorry, read. Okay. For import, it's going to be read, because you want to read the data from the disk. So you send the read command, and then mostly you're going to tell, the IO say, okay, which blocks you want to read, okay, and also which memory location you want to eventually save this, this block into. So you're going to say block ID. So M is the memory location, and which block you want to read. Okay. So you send that information. So then when the controller find out, okay, so I received the data from my registers, like opcode. Oh, it says read. And the operand, it says, oh, which block you want to read from. So then the block N, the particular block, the data will be copied from the disk to the buffer. Okay. When the copy operation complete, and then the controller gonna set the status register. Say, okay, the copy is complete. It's successful. And then while the controller is actually doing this copy process, the CPU gonna be always checking the busy register. Okay, because when actually controller is doing the copy, you're gonna set the busy register to true. So that means I'm busy. So then the CPU gonna keep pulling the data from the busy register. So that's the reason why we call the program IO with pooling, because the CPU gonna periodically, running this driver. The driver gonna keep pulling this data. Okay, pulling the data from the busy register. Say, are you busy now? Are you busy now? And the controller say, I'm busy. And suddenly, when controller finish the copy and set the status to complete, and then set the busy back to false. So that means I'm free now. So the next round, when the driver actually check the busy register and find out it's false, so then it will copy the data from the buffer to the memory location. And once it's done, and the CPU going to check the busy register again. So are you busy? It's not, then you're going to actually copy the opcode and operand to the opcode register and operand register. And then the process, continue. So that's basically how does this does. Now, if you have the program with interrupt, it's basically the same as the pooling, except, once the actually CPU check the busy register, say it's false. That means it's not busy. Then you're gonna put everything in the opcode, the command in the opcode, and the data in the operand. So then the controller gonna set the busy register to true. So that means I'm busy, and then start to do the job. And while the controller is do the job, and then the driver will actually block itself. Okay, so you're gonna put himself or herself into sleep. So in that case, the CPU is gonna do something else, because the driver is not running. So now once the controller finished the job, the controller gonna send the interrupt to the CPU, say, I'm done. Okay, and then the CPU basically check the busy status, check the status register to see whether the transfer is successful, and then start to process the data from the buffer. Okay, so that's the interrupt. That's the only difference between pooling and interrupt. Anything else is pretty much similar. Okay. Now we mentioned that for pooling, we compare the pooling and the interrupt. Now pooling is actually good for any kind of operation which is very quick, particularly for the I/O device, which can actually process data very quickly. For fast I/O, pooling is good idea because the I/O only going to take like a couple of microseconds to complete the job. So the pooling going to actually, while actually the I/O is doing the job, the drivers keep pulling data, pulling the actually data from busy register. Okay, but that time is very short because the I/O going to take a very short time. Okay, now if the I/O is very slow I/O, so the I/O going to take a very long to do the job. Some kind of I/O device is very slow. For example, uh, like a printer. So when you send the command to the printer probably going to take like a couple of seconds or even a minute to complete the printing job. Now, once the job is printed, then you're going to actually interrupt the CPU saying, okay, I'm done my printing job. So what's your next request? Okay. So in case like a printer, it's a very slow I/O. So then interrupt is the best idea because while the I/O is doing its job, like a printing some kind of pages. So in this 1 minute, like while the I/O device, the printer is busy, CPU is not going to do anything related to it. CPU going to actually switch to other processes and doing some other job. Okay, so that's why interrupter is good. And when the printer finish its job, then it can send the interrupter to the CPU. Okay, so that's something we just talked about last time. And here's a diagram which basically illustrate two kind of scenario. Okay, now the last case we mentioned is the DMA. Okay, it's called direct memory access. Now DMA is actually, it's a kind of a dedicated device. It's also connected to the bus. Okay, when the CPU requests for anything, say, could you please do something like if you want to make, display a movie. So in that case, it depends on the application. CPU then going to program the DMA, say, okay, so for the next couple of requests, you actually take care of it. So the DMA actually take over the role that CPU actually used to take. So DMA is just like a small scale CPU. Okay, it can take over CPU's job. CPU is a general purpose CPU, so it can do a lot of work, but DMA is dedicated to CPU. So it's not as powerful as CPU, but it's okay because DMA is not going to actually deal with all these different multi-processing thing. It's just actually doing some dedicated job. So it doesn't have to be very powerful. So that's the DMA. Okay. So these are the difference. Okay. Now the pink actually color basically represent how much CPU time just wasted. Okay. Now using the I/O with pooling. Now for slow device, I/O pooling a slow device. That's a not really good idea to use pooling for slow device, as we mentioned that, when actually application make a request to the device and device actually start to do its job. Okay. Now during this time, this application gonna keep actually pulling the data. Just check the busy register. Say, are you free now? Are you free now? Are you free now? And the device say, the busy register is always true. So that means it's not free. So it just wastes another cycle. Okay. Now in multi-programming environment, maybe the CPU gonna actually allocate a certain portion of time to this particular application for using the I/O device, and then it's gonna switch to other processes. Now, when it's turned again for the application, now the I/O device is still not finished yet, so you just do the continue to pull the information from busy register, and it's not done yet. Okay, so these CPU times are wasted. So every time, actually, when in the multi actually programming environment, every time when the CPU allocate the time to this application, and this application is mostly just doing the pooling, just doing this infinite loop. Okay, and then so when the time slot actually changes to another processes, then CPU is doing something else. When CPU comes back, well, this device just finished the job, right? So it's finished the job over here. So the device has completed the job, but at this time, the CPU is dealing with other processes, not with this particular application. Excuse me. So during that time period, device is wasted because the busy register becomes false. Okay. So, but the application is not pulling the busy register now until it's time again for this process to use the CPU. So then it just pulled the data and then find out, oh, the CPU is the status register say, okay, it's completed successfully, and the busy register say, okay, it's false, I'm free. So then the application can actually basically copy the data from the buffer to the memory. So it's doing the job. Then once it's done, then it can actually send a request again to the device, say, could you do me a favor to do something else? And then the process repeat. Now during this time, every time that allocated to the CPU allocate to the application, its time is wasted. Most of the time it's just doing the pooling because the device is so slow. Now in that case, for the exactly the same case, now for this slow device using interrupt, then so CPU basically pull the busy register and find out it's available, and then the CPU can actually the process can actually start to actually doing the job, and then once it's done, it just actually block itself. So it's not going to use the CPU. So CPU going to completely doing some other processes, not this application. Now, when the device is done, then it's going to send the interrupt. Okay, so it's an interrupt handler, send the interrupt, and then the process is actually is triggered, and it's waked up, and it's start to do the job again. So during this time, no CPU time is wasted, but the interrupt itself takes some time, but that's okay because the interrupt time is like this, but the whole block time is much longer than the interrupt time. So it's worthwhile to do the interrupt in this case. Okay, so that's pooling versus the interrupt. Okay, now here's the last topic I'm going to cover for this class. So in this section, we've actually talked about the data buffering, okay, and the caching. Now remember, in each of the device, talk about, there's always a buffer, right? So buffer is actually a place, a register area, a storage area that used to transfer the data between I/O and the and the memory. Okay. So there are a couple of different type of buffer. A buffer is a register or an area of main memory used to hold the data generated by the, either by the producer process or removed from the buffer at a later time by consumer processes. Okay. A process that actually basically produce the data and put it into the I/O, we call the producer actually process. And the consumer basically just doing the read command, just everything, just actually the controller, the I/O controller, put it in the buffer, waiting for the consumer process to access it. Okay, so that's two different processes. Okay, so one of the example of producer process is the process that basically doing the output. Okay, the consumer process is doing the read. Okay, that's the producer. So the producer basically gonna write the data, into buffer. So then the controller gonna actually copy the data from the buffer to the device, right? So remember this. So this is a buffer controller. Here's the buffer. Okay, here's the I/O device. Okay, so the producer always write the data into the buffer, and then the controller actually can copy the data into the I/O device. If it's a disk, then it's going to copy the data into disk block. Now the consumer basically always, read data from buffer. So normally, once the CPU requests the controller to do something, the controller asks the I/O, say, please send the data according to the request. And the I/O the controller gonna get the data and store in the buffer. And then the consumer gonna actually then consume the data. Okay, so that's consumer. Okay, we just use two different terms to describe a different type of processes. One is producer, one is consumer. Now, one of the data type is, we call it um, single buffer. Okay. So single buffer is kind of buffer. You can hold one character at a time or a large block of data. So the single buffer basically means, for example, like in a controller, any controller, most of the controller, like a busy register, it's actually a single buffer, right? And a status controller, it's a single buffer. And so you can interpret like this. So it's a single buffer. But single buffer basically means when a producer is actually write the data into the buffer, the consumer cannot do anything to the buffer. So the buffer is shared, but only used by one, either by consumer or by producer, not both. Okay, so that's called a single buffer. Okay. Now here, let's take a look at one of the example. So the keyboard buffer. Okay, so the keyboard basically generates characters one at a time, but a user process may wish to receive the data only as complete line. So that means if I have a keyboard, so I type the data, I type any of the data. So the keyboard is going to send to the controller. Okay. So then, so here's a buffer. And then connected to something else, like a memory. That's a bus. So now, once the actual command is sent, say, okay, please actually, you know, just type the data. So every time I press the key, so like A, so that the data A will be stored in the buffer. I send a type of B, and B will be stored in the data. So until the buffer is actually probably can contain, for example, 16 characters. So once the 16 characters is full, that once the buffer is full, that means all the 16 characters are actually, in place. G or whatever. So the total actually buffer is actually completely full. And then the data will be actually sent to the memory. So A, B, all the way to G. Okay. So when you fill the buffer, the producer fill the buffer, and then the consumer is not going to consume the data. So once it's complete, okay, then the keyboard basically interrupt the CPU, say, okay, I'm done. The buffer is full. Please take the data, and send the CPU basically copy the data to the memory. So the buffer going to be used either by one side or the other side, not both. Okay, so that's basically a single buffer. Now in the keyboard case, there are two type of keyboard. One, there are two type of actually buffer. One is so in one case, so when you actually type anything, any character, and this character is going to be copied to the buffer. Type another character, copy to the buffer, and then I find out, oh, I got something wrong. So I need to actually type the reverse button. Okay, so to backup button to actually delete the previous character I just typed. So then in some case, the data will be deleted in the buffer because you press the backup key. Okay, so and then eventually when the buffer is full, the data is copied to the memory. In that case, so whenever the driver who actually can do the correction and correct the data in the buffer. Now, before you send the data from the buffer to the memory, the data is actually the final result. Now, that kind of driver is called cooked data mode. Okay. Now, in another case, when you type any letter, say A, B, and then I find out B is wrong. I don't actually mean to type A and B. I mean type A and C. So in that case, you type a backup key, and then you type C. So in that case, now the driver will not correct the data in the buffer, but record the operation in the buffer. So that means when you type A is actually sent to the buffer. Type B is sent to the buffer. And then I find out, oh, B is not right. So I type a backup key. And this backup key is also sent to the buffer. And then I go to C, type a C. So in that case, the data stored in the buffer it's uncooked. It's called a raw data mode. So in another case, the driver passes all characters to the application unchanged. So basically, the driver does not interpret the backup key. it just record, say someone just press the backup key after B, and then the application they're going to interpret it, say, oh, B, then backup. So that means B should be erased. Okay, so then it will be corrected in the application. So these are two type of single mode buffer. Okay, so this is actually the raw data import mode. So if I type, say, test, okay. So I type T and I type E, and basically what I want to type is text. Okay, so I type T, that's correct, and then I press E, that's correct, and then I press S, that's wrong, right? But I did not realize it's wrong. So I continue to type the next character T. And then I realize it's wrong because that should be S. So then what I'm going to do is I'm going to press the backup key. Okay. And then I'm going to, press the backspace. Okay. So I just basically back one character, but not to erase. And then this is backspace. So that means I actually erase. So back. So that means if it's I type txt, so that means if I type it back, so the cursor going to be here. And then when I type bs backspace, then I erase that x. Okay. And then I type x. So I just replace with x. Okay. And then I press forward key. Okay. So that means I'm going to move forward. So eventually, so it's going to be corrected itself. But that's a raw import mode. So every time when I press the backup key, backspace, and then when I do the correction, the controller does not do the correction. It just record all the operations, including the correction operation. Now cook the import data. So the controller going to interpret this. Okay. So when you press the backup key, so it will be actually just go back in the buffer. And then when you click the backup space, and you're going to erase the S. And then it type X, you're going to insert X. And then if move forward key, then you're going to move back. So after you finish all this operation, so in the buffer, it's a TEXT, and the cursor is actually moving here. So these are the two different type. Okay. Now, this is actually for the single buffer. So it's shared by the process that write the data into the buffer and the process that read the data in the buffer, but they cannot be operate at the same time. So that means the producer and the consumer cannot operate at the same time. Now the second approach is, in this case, the problem with the single buffer case is it's shared by producer and buffer, but cannot be, operate at the same time. Now, what's the problem with this? Now, if the producer actually produce the data and put the data into the buffer, and the consumer immediately consume the data, take the data off of the buffer is empty now. So then the producer can put the next data into the buffer, and consumer take the next data into the buffer, out of the buffer. That's okay, right? What about the producer put the data in the buffer, and the consumer is so slow, it failed to take the data out of the buffer? Then what the consumer gonna do? Oh, I'm sorry. I think I just do the opposite. when the producer produced the data into the buffer and the consumer failed to consume the data out of the buffer, what the producer going to do? Sorry, I just actually move backward.
Will the producer have to get blocked until the consumer can take out all the data?
Producer either going to be blocked, or if like the pooling case, the producer keep actually pull the actually the buffer. See, are you ready? Are you ready? Right. So either way, producer is not gonna do anything. So that's the problem with the single buffer. So if you actually have a very fast producer, a very slow consumer, this single buffer is not going to work. Okay. Or if the producer produces the data, consumer does not consume the data, that's not going to work. So the buffer swapper is another kind of design for the buffer. So in this case, when producer-consumer situation sharing a buffer, the consumer is blocked or idle while the producer is feeding the buffer. Similarly, the producer is blocked or idle while the consumer is copying the data. So either way, one is working, the other one has to be stopped, or just keep pulling, whatever. Now, the buffer swap is a technique that allows the operation of the producer process the buffer process and the consumer process overlap by using two buffers. Okay. So now the producer going to fill this buffer and the consumer hopefully can consume the buffer. Okay. So then this buffer is actually full and this buffer is empty. And then swap. Okay. So now the consumer can actually then switch to this buffer and the consumer producer switch to this buffer and the consumer can actually to actually consume data from another buffer. So the consumer and the producer can access the buffer at the same time. But because you have two buffers, the producer going to access one buffer, the consumer going to access the other buffer. And once their job are done, and then the buffer actually, the role of the buffer swap. And then the producer going to access the other buffer, consumer going to access the other buffer. And once it's done, and the swap back. So you can actually keep swapping. So that means at least you have some kind of room for the consumer and the producer to work at the same time. So there's some kind of overlap. So this is going to save some time and reduce the CPU waste, or at least reduce the, make both actually producer and consumer busy, But still, this buffer swapping does not solve this problem. If the producer is faster and the consumer is slow, then once the producers, produce the item, and the consumer is still consuming the other buffer, it's not done yet. So both buffer is full, and the producer has to block, itself until the consumer finish the other buffer, and then then swap, and the producer start to actually fill in the empty buffer, and the consumer start to actually consume the other buffer. And again, if the consumer is slow, then producer quickly fill the buffer and is still going to block itself. So that's the problem. So the buffer swapping is a technique and allow both producer and consumer work at the same time, but still does not address the problem of faster producer and a slow consumer, or vice versa. So this basically diagram gave you the idea of when we use a single buffer. So the producer and the consumer are going to do alternate. Okay. When producers fill the buffer, consumer is actually, just to pull the buffer, and it does not do anything. And then once the producer finishes the job, and the consumer basically copy the buffer, and the producer cannot do anything until, you know, consumer completely empty the buffer, and then producer can fill the buffer again. So you're gonna do the alternate. Okay. So either one of these gonna be idle, the other one is working. Now, in this case, if the producer and consumer actually work at the same pace or almost the same pace, so initially, when the producer is filling buffer 1, consumer is just to try to pull the buffer 1 until producer finish the buffer 1, and then the consumer say, tell consumer say, I'm done. So the consumer start to copy the buffer 1. While the consumer actually start to copy the buffer 1, consume the data from buffer 1, and the producer is not going to stop. Producer can continue to fill the buffer 2. Okay. Now, hopefully, when the consumer finish the buffer 2, now the consumer may or may not be completed yet. Okay, so in this case, the consumer is still actually copy the buffer, but not very long. The producer does not waste too much time, because after a small period of small waiting, the consumer actually finished the buffer 2. I'm sorry, the consumer actually finished the buffer 1. So the buffer 1 is free, so the producer can continue to fill the buffer 1. And then the consumer start to copy the buffer. Okay. The ideal case is producer fill the buffer, and the consumer copy the buffer 1, fill the buffer 1, copy the buffer 1, and the producer fill the buffer 2, and then consumer basically copy the buffer 2, and the producer gonna fill the buffer 1 again. If they actually take the same amount of time to work on each of the buffers, then that's the ideal case. But in some case, there's some, time difference. Producer, in this case, producer is a little bit quicker than the consumer, right? So producer finished the filling the buffer, but the consumer is still actually copy the buffer 1. And then in this case, the consumer is faster, complete the copy the buffer 1, buffer 2, but producer is not ready. Okay, still filling the buffer 1. So there's some inconsistency, but the time just wasted is not really that big, because you have 2 buffers, so they can actually swap, between buffer 1 and buffer 2. But it's still not going to solve the problem when the consumer is much slower than the producer, and the producer, it end up that the producer always going to wait. Okay. Now the circular buffer going to solve some kind of problem. Now circular buffer is almost like a swap, but you have more buffers. Okay. You have an array of buffers. You have buffer 1, buffer 0, buffer 1, buffer 2, buffer 3, buffer 4. Okay. So the producer and the consumer here, producer going to actually fill the buffer 1, and then move to next one, fill the buffer, fill buffer 0, and next to fill the buffer 1, next to fill buffer 2. Okay. And then the consumer start to consume the work. Okay. Now take the things out of buffer, and then take the product out of a buffer, and then take this out of buffer. Hopefully, while consumer is actually consume the product, producer going to continue to move on. Once consumer actually finish to the end of this array, so because consumer already finished empty the buffer 0 and 1, so the producer can actually start over again. Okay, so that's why you can treat this 0, 1, 2, 3, 4, the array of buffers, as a circular buffer. Okay, now you can actually interpret this like a circle. Okay, so buffer 0, 1, 2, 3, 4, and the consumer basically gonna producer gonna actually produce the things and put in the buffer, and then move to the next So the consumer gonna move to this direction, okay, and a producer, and the consumer actually follow this. So looks like in a circle, producer and a consumer just chase each other. So producer can continue to produce and fill in the buffer, and consumer actually follow the producer and consume the buffer. Okay. Hopefully, if both consumer and the producer, they're never gonna catch each other. So in this case, both consumer and the producer gonna be busy, right? If they don't catch each other. But if the consumer catch the producer, so that means consumer consumes much faster than the producer can produce. Or the producer just catches the consumer, so that means producer can produce much faster than the consumer can consume. So in both cases, one of the process has to wait. But the ideal case is because you have enough actually buffer. So even though sometimes the producer is faster and sometimes the consumer is faster, you have enough buffers to make them both busy. So no one gonna catch the other one. The consumer cannot catch the producer, and producer cannot catch the producer. So they both actually working on these actually circular buffer. So that's called a circular buffer. Circular buffer is really good. It can solve some of the problem. You can think about a buffer as a warehouse, like a Walmart. Say Walmart, they actually have a warehouse. A warehouse is a buffer. So when Walmart actually order the product from the vendors, they fill in the warehouse, and then on the other side, when Walmart sells the product, so they're gonna empty the warehouse, and so one side they fill the warehouse, the other side they empty the warehouse. So a good warehouse is that the warehouse is never going to be full or never going to be empty, because if it's full, then the consumer has nothing to consume, right? If it's empty, if it's empty, the consumer has nothing to consume. So that means the warehouse is empty. They sold every product, so the customer cannot get any product. If they want to buy, they cannot get the product because the warehouse is empty. Now, if the warehouse is full, so then the producer cannot fill the product anymore. So that means the sale is very slow. They are not going to sell a lot of product because the warehouse is completely full, and still no customer actually buy any product. So the idea, the very healthy actual warehouse is that on the one side, you're going to constantly empty the warehouse and take the product, and also in the meantime you can constantly fill in the warehouse. Okay, so that's the best thing. Circular buffer is designed for this. Okay. So I think that's the last topic I want to talk about. It's a disk block caching. Now, if you buy any hard disk, there's always something called a cache. Okay, so if you buy a hard disk, which is like a 1 terabyte, most likely you may have a cache of 64 gigabyte. Okay, so these cache space, cache is actually a buffer. It's the cache space basically used to store a frequently used blocks. Okay, so the data actually stored in the hard disk in terms of block. Okay, so which is actually connect to the controller. Okay. And then connect to the bus. Okay. So the operating system may maintain an additional large cache in the main memory. So main memory has a cache. Sorry, the cache is not here. It's here. Now, what is the cache? Cache is actually a kind of temporary storage that every time when people try to actually access the data in the memory in some device, okay, so they're going to access the cache to see that is the data still in the cache. If the data is not in the cache, then they're going to go over to the memory. Okay. So a disk block cache is a set of main memory buffers that contains the most recently accessed data block. So for example, if a driver just say, please access a particular block, data from particular block, a couple of blocks. And then, so they first are going to actually, when the driver do this, so then they first are going to actually check the disk block cache over here to see these data in the disk hard disk block is still actually in here. If it's in here, they are not going to actually directly go to the hard disk to access the data. They just copy the data from the cache to the memory. Okay, so the cache basically can actually store the recently accessed block. So basically, if it's not in the cache, the data actually, the driver tried to access is not in the cache. So then it's going to copy the data to the memory from the disk. But in the meantime, when they copy the data to the memory, they also copy the data, the blocks into the cache. Okay. So next time when they try to access the same, read the data from the same blocks, they first read the cache. If the cache still contains the data, they copy the data from the cache instead of from the hard disk. So cache is some kind of a temporary space. Now, cache is a very, very useful concept in the computer system. So every device has a cache typically, Now, even like, so one of the example for the cache is, when you actually try to access a website, a web browser, try to access the web page. So what they're going to do, the computer, actually web browser going to do is, web browser going to first check a space called a cache space. And we call this space like a cookie. So the cache space, they're going to check the cache space to see, did I access the website before? And is this website still in the cache? If it does, I'm not going to go all the way to the web server, which is actually located 1,000 miles away. So I'm going to directly access the web page from the cache, or we call it cookie, and then copy this web address to the browser. So this is going to save some time, because if you try to access the data from a remote server, this is going to be very time consuming. Now, people are going to say, how do you know if I try to access the data in a hard disk? And how do I know if you try to access the cache, how do I know the data should be in the cache? The answer is no, I don't know. But, this is actually, the cache concept works very well. Why? Because this is actually something, something that is always true in our life, in our daily life, or in most of the computer system. So this is based on some kind of statisticals. the statistical basic typically say, if you actually access this particular data in the hard disk, then most likely you will access that data again. Okay, so if you access the particular data block in the hard disk, you copy data to the computer active memory, and so most likely you're going to access the same data again later on. Now, if that's the case, why I just actually copy when you access the data in the first time, why I just copy the data in the cache, and next time when I access the data, I don't have to access from the hard disk. Instead, I access it from the cache. Okay, so this is always true. This is actually very interesting. Okay, by statistics. Now, the same story happens. For example, if you have, I can tell you, if you have a desk, you're going to work on your paperwork. So then when you stop your working, you're going to put your paperwork on the desk. Say, okay, I will actually work on this paperwork again tomorrow or in an hour because I'm busy now. So I'm going to come back and continue to work on this document. So I put on the desk. Now, then you work on something else. And then suddenly time's up and you say, oh, I'm not finished that yet. So I'm going to put this work on the desk again on top of the other paperwork. So now the truth is, if you put something on the desk and you claim I'm going to work again on this document, but you never actually, if you forgot, so you did not work on this document. So it's on the paper, it's on the desk. And then you have more work to do, and the more work you're going to actually put on the top of this. So eventually, you will never actually go back and work on this paperwork. So same story is if you're in a party and you meet someone in the party and you exchange the business card, say, I'm interested in you, so please call me again. So you get the phone number from the other guy. And next day you call that guy, okay? So, or you get the card, the phone number from this guy, and they say, okay, I will call you back. And then you did not call this guy back next day. You did not call this guy in 2 days. And then you did not call this guy in a week. And most likely, you're never going to call this guy. Okay. So so that means if you actually say you want to call this guy and you call this guy next day, and then you most likely you're going to call this guy again. So the frequently accessed data will be accessed again. So that's the concept. So that's the idea for the cache. Okay. So the cache idea is frequently access the data will be always in the cache. So if you actually access the data, same data again, don't actually go to the hard disk, just go to the cache. So that's basically the idea for data blocking cache. Okay. So I think that's pretty much all I want to talk about. So I'm sorry because that's probably all I can cover for this semester. But I think we pretty much cover all the materials we want to cover. We talk about the processes, we talk about memory management, we talk about file system, we talk about the I/O. So particularly, I think the process and the memory, these are the big part of the operating system, and I/O is also. But you may have different I/Os, but the concept for different I/Os are the same. There's only two different types, a couple of different types. One is the slow I/O, the other one is fast I/O. For slow I/O, I think programmed I/O with pooling going to work well. For the fast I/O, for the slow I/O, the I/O with interrupt, the programmed I/O with interrupt will be better. Now, if you're going to repeat these I/O jobs for a long period of time, it's always better to use the DMA, the I/O DMA. Okay, I/O with DMA. So you actually CPU offload its job to DMA. So the DMA gonna deal with the job. Okay, I think that's pretty much all I want to talk about for the whole semester. And now, first, I have to apologize for one thing, because this is again a very interesting semester. So so we have COVID-19, so we cannot meet for each other, even though I talk to you on the Google Meet, but we never have physically met in this semester. So so that's the reason why I actually used the Zybook for the first time. I never used the Zybook. I always use some other books. I always provided my own material, but unfortunately, because of the COVID, so I actually start to adopt the Zybook. And then actually I find some good things about the Zybooks, because the Zybooks has a lot of, it's a web-based book. So it has a lot of actually very good features, like these ammunition things. I like it. You cannot play an ammunition using most of the physical textbook, right? So this is good. Okay. So I hope that you're gonna find out this semester is very useful. I will be relieved if I think so. And also, I hope that if you have any feedback saying, okay, for this remote teaching, this online synchronous teaching, you know, just let me know if you like any of this, or you dislike any of this. You know, just give me some feedback if you want. You know, I appreciate your feedback. And I also appreciate your patience, because sometimes it's kind of frustrating. You know, this is technology. Because in the regular class, if you have any issues, you can actually come to my office. But here, my office is virtual. So okay. So, but anyway, we finally made it. And so keep your good working. So I hope your good luck in any other classes. And just keep that in mind. If you actually missed any of the work, I always accept a late submission. So even Zybook says, oh, okay, you are late, and I'm not going to count your credit. I'm not actually, but I'm actually, you can still work on these exercises on the Zybook. And once you finish any of this, please send me an email. Let me know. I will actually give you some grade. But as I said, in the syllabus, there's actually some penalties for the late submission. That's always the case. Okay. So if you submit late, there are going to be some certain percentage of penalty. But it's still, you can still get most of the grades. So please don't give up. Okay. I think that's pretty much all for the whole semester. And so the final exam is on May 11th. Please check the Blackboard for the details.
Thank you, Professor. It's been a pleasure this semester.
Okay, my pleasure.
Have a good summer.
Yeah, just send me a feedback, anything, email. Just let me know. Okay, so good luck.
Have a good one.
Have a good one.